Now we're going to turn our attention to factoring special types of products. So these are going to show up frequently in several different forms, but one that we will encounter are perfect square trinomials. So an example of this would be if you had to factor or expand expressions like this. A plus b squared is just a plus b times a plus b. And filling this out, we're going to get a squared plus ab plus ab, so that'll be plus 2ab plus b squared. And the other type would be a minus b squared. So that would be a minus b, which would be a squared. And that would be minus ab, so that would be minus 2ab, and then plus b squared. So if we were given expressions like what's on the right here, and we wanted to factor, so the factorizations of perfect square trinomials, well, that's just going from the right to the left. So if I were given the expression a squared plus 2ab plus b squared, and we could recognize that that's a perfect square trinomial, then we would just factor this as a plus b quantity squared. And similarly, a squared minus 2ab plus b squared, we can recognize that as a perfect square trinomial and factor that as a minus b squared. So these are perfect square trinomials. And the form is actually pretty quick to recognize. And so if that's the case, then the factorization should also be quite quick. And we will see that it actually is. For example, this first one right here is x squared plus 10x plus 25. So if we use the previous procedure to factor, that's perfectly fine. But notice that the first is this x squared, it's a perfect square, and the last term is a perfect square. 25 is 5 squared, right? This is 5 squared. So it has this form here, a squared plus 2ab plus b squared. So what does that mean? Well, that means that it's going to factor like that. What is a? A is x. And what is b? B is 5. So x plus 5 squared. That's the factorization. Right? And indeed, if you were to expand this out, you can check, but that's going to work. Okay, x plus 5, x plus 5. You don't have to do that check unless I specifically say to. That's optional, but if you ever have extra time and you're worried, you can always do this. Or if you're definitely unsure, you should do that. But that's 10x plus 25. So definitely looks good. Okay, and you can't just look at this and say that's a square and that's a square. You have to make sure that the middle is definitely of that form. Do you see that that is 2 times 5 times x, right? 2 times 5 times x. So this is of this form right here. Okay. You know what? I'm going to keep this boxed and just a little bit separate up here. Our second example, we have the expression 36, which is a perfect square, that's 6 squared. And a squared is a perfect square, that's a squared. And then what is this? Well, that is minus 2 times 6 times a. So it looks like this is of the form right here. It's not written in the exact order, and since I'm using a, it's not this a, but do you see that we have something squared minus 2 times the base of the squares for these two, and then this is squared. So what would the factorization be according to this? Well, the a for this is actually our 6, right? And what's our b? Our b is the a here. So this is minus a squared. And you can check this really quick. So 6 minus a squared is 6 minus a times 6 minus a, and that would be 36 minus 6a minus 6a plus a squared, so that's 36 minus 12a plus a squared. And is that what we had over here? Well, 36 minus 12a plus a squared, so yes. Okay, so that looks good. Our next one here, we have 64, and 64 is a perfect square. This is 8 squared, and t squared is a perfect square, right? That's t squared. There's no real reason to write that under there, but do you see that this is 2 times the base of each of these? So 8 is the base, t is the base, so 8 times t, right? So when that happens, that is of this type up here, this perfect square trinomial, and everything was addition in that one, so we have this first type. So what we're getting is that this is just 8 plus t squared. And we can always check this. Don't have to, but doesn't hurt to actually just see this extra check. You know, the square would look like this. So 64 plus 8t plus 8t plus t squared, which is 64 plus 16t plus t squared. And that is what we originally had. Another type of special product that shows up quite frequently is something of this form right here. So the difference of two, this is something called the difference of two squares. So the difference two squares. So if you have a product of the form a plus b and a minus b, when we FOIL this out, we'll have a squared minus ab, and then plus ab, and then minus b squared. So you actually see that the middle terms cancel, and you actually just have a squared minus b squared. So this is why it's called the difference of two squares. So the factorization of a difference of two squares is just the reverse of this. So we have a squared minus b squared, and that's just going to factor into this nice form. So you have a plus b and a minus b. So if you look at what we have over here, we have x squared minus 16, and these are both squares, and we have a difference of two squares. So this is x squared, and this is 4 squared. So we have this difference of two squares. So we're simply just going to get x minus 4 and x plus 4. This is actually probably one of the simplest types of factorizations that you can actually have, and it shows up quite frequently. All right, so that middle term is actually gone, and we just have a difference of two squares, and that's the factorization. You could check that real quick. We'll have x squared and then plus 4x minus 4x, so those middle terms cancel, and we're just left with minus 16, so that is definitely correct. This next example, well, we have a fourth power of x, and we have minus 16. So is this actually a difference of two squares? Well, can you write each of these as are they squares? Well, x to the fourth is actually just the square of x squared, right? X squared times x squared is x to the fourth. So that is a square, and 16 is 4 squared, right? So this is still a difference of two squares, and the factorization will be x squared minus 4 and x squared plus 4. And we can, of course, check that if you're ever concerned that you're not getting the correct factorization. And since this one is slightly different, why don't we check that real quick? So x squared times x squared plus 4x squared minus 4x squared, and then minus 16, right? So these two cancel, so those are gone. But then x squared times x squared is x to the fourth and minus 16, and that's exactly what we originally wanted to factor, so that's perfectly fine. So you can still use this different difference of squares as long as you can rewrite what you have as a square, right, for each one. It's very recognizable when you don't have middle terms. Now, unfortunately, when you see examples where you have cubes and odd powers, then you can't just explicitly write those as perfect squares like we did before, right? We can't write x cubed as a square unless you allow fractional powers, but we're going to have to do something different. And another type of special form that comes up is the sum and difference of two cubes. So the sum and difference of two cubes. All right. Now those can be expressions with cubes as well, but if you ever have something like a cubed plus b cubed, we can always factor this as a plus b, and then we'll get a trinomial actually. So this will actually be a squared minus ab plus b squared. Okay, so the cubic factors as a binomial times a trinomial like this. And similarly, if we have a difference of cubes, we can also factor that as a binomial times a trinomial. So this will be a minus b and then a squared plus ab plus b squared. So this example here, we have a sum of two cubes. So this would factor as x plus y, x squared minus xy plus y squared. Now, if you wanted to, you could expand this using the distributive property and check that, and I encourage you to do that. That would actually be good practice for the previous section. But right here, we have these formulas that we can use, and so we're just going to use those. So in this last example here, we have a cubed minus 8. So can we factor that? Well, this is a cube, right? This is a cubed, and we have minus 8. So if the 8 is also a cube, then we'd have a difference of cubes. Well, 8 is 2 cubed, right? 2 times 2 times 2 is 4 times 2, which is 8. So 2 cubed is 8. Difference of cubes, so we can use the above formula that we have for difference of cubes. So this one right here. So what are we going to get for the factorization? So we will have a minus 2, right? So the a is, so here a is a, right? And the b is 2. So we'll just replace all those things. So a squared plus, so if b is 2 and a is a, then we have 2a, and then plus 2 squared, which would be 4.